Good afternoon, everyone. Thanks for coming. In this talk, I'm going to briefly describe some of the patterns that you may want to consider when building your real-time or batch processing pipelines. Quick 1-minute introduction about who we are. We are an IoT-based platform. What this allows you to do is that your devices can talk to other devices in a secure way, and this is being done in a manner such that it's independent of the underlying wireless or any of the transmission protocol. As far as the ingestion goes, we support various kinds of protocols, being HTTP, WebSocket, MQTT, or CoAP. Let's look at a couple of examples to see which protocol might make sense. Say I have a smartwatch and say it has a bunch of sensors embedded in it. Such a device may be collecting data points related to, say, heart rate, ECG, or PPG, or maybe your skin temperature. It could be any of your body metrics. Such a device could be generating data points that is of the order of 100,000 plus data points in a very short period of time. You would want to use WebSocket in that case. If I have a device that has low processing power, you would want to use CoAP. Maybe it's a microcontroller. And as far as the ingestion goes, we collect various kinds of data, be historical or continuous or discrete. We have a powerful rule engine to augment real-time alerts and actions. I will go over the tech stack in my next slide, but it enables you to send real-time alerts. The pain point right now in the IoT space is that a device cannot talk to the other device in a secure way. We are trying to solve that problem, and hopefully everything goes fine. This is a quick slide, and if you want to learn more about Arctic Cloud, you can go to arctic.cloud. This is about me. A quick slide about our backend stack. We are a JVM shop. Most of our code base is in Scala. We use Apache Mesos for deploying most of our stateless services through Marathon. Our microservices are based on Play framework. We use MySQL for managing our entities. We use Apache Cassandra to manage all the time series data, and we augment that with Elasticsearch to answer some of the dynamic queries. The challenge here is how much you duplicate in Cassandra versus you go in Elasticsearch. So you have to make some choices there in terms of performance, something to consider. Messages within our pipeline are mostly encoded in Avro or message pack format, so that you spend less time on serialization. We use Apache Parquet for storing structured data in HDFS. Our batch jobs are mostly written in Apache Spark. As far as the stream processing frameworks, we use SAMSA and Spark Streaming. We are in the process of evaluating Apache Flink. We have some computations and transformations that's based on event time, and we want to use Apache Flink for that use case. Our rule engine is based on SAMSA, Akka cluster, and Akka streams. For data sets that fit in memory, we use Redis. I'm going to talk about, since this is a 20-minute talk, I will briefly touch upon a couple of frameworks that we think we like it. The first one that I want to talk about is Apache Parquet. Apache Parquet is a columnar storage format that enables greater efficiency in terms of file size and query performance. It's originally based on Google's Dremel paper. The advantage you get is that your file size is much smaller than what the row-oriented equivalence would be. If you are dealing with hundreds of terabytes of data sets, this adds a huge value here. It could be even 30 to 40% of savings. When you're running your software on AWS cloud, this does matter. It does. Now let's discuss how it's able to achieve the storage savings. It does this by storing the columns next to each other, which allows very efficient encoding techniques. The first encoding that it applies is the dictionary encoding. Dictionary encoding, what it does is it takes your arbitrary long key text and encodes them into a small value, small int, thereby saving storage. Delta encoding can be used for temporal data, wherein it is sufficient to just store the first entry, and the values from 2 to n, it's sufficient to store the differences. You can use run length when you have contiguous duplicate data, wherein it is sufficient to store the first value and the first unique value and followed by the number of duplicates. By applying all these encoding techniques, you realize savings in storage. To convey the point, say you have your actual records. Okay, I guess I need to be closer. Say the first table lists the actual records, and your row representation, each record would be placed one after the other. In a columnar representation, the columns are placed next to each other. Now the data is homogeneous, and you can apply these efficient encoding techniques. It also makes your data more cache friendly. There is less misprediction in terms of branches, so your jobs will run much faster than the traditional sequence file counterparts. The cool thing about Apache Parquet is that it allows you to store deeply nested structures in a columnar fashion. What this means is that your existing applications can continue to use Avro, Thrift, or maybe raw JSON to send the data inbound. I highly recommend you use a serialization formats such as Avro or Thrift so that you save less on serialization costs. If you use Apache Avro, you have the advantage that your data and the schema can evolve in a backward compatible way. What this means is that, hey, I made a schema change and now I broke my bad jobs. You wouldn't want that. You would like to know the failure right before, say, you queuing the event. So far we talked about the storage savings. The next advantage that you get is your query performance. With Apache Parquet, the query engine can skip over columns that are not needed to answer a query. It does this by pushing your predicate and projection pushdowns all the way down to the storage layer, and thereby saving on I/O costs. And here is an example. Say I'm collecting a body metric, and this is an Avro schema. Say I have device ID and device type, which I have marked it as mandatory. ECG and PPG2 are optional. The device might or might not emit them, and the channel is mandatory here. So this is the row representation, and now the columnar equivalent is as follows. The syntax is very similar to protobuf. Things that are being marked mandatory here, say device ID or device type, there is this prefix called required, and for optional ones like ECG, there is this you need to put in that optional keyword. String is, as you have seen here, string is a logical type in Apache Parquet. The internal representation is that it's stored as a binary with UTF-8 encoding. So this example shows us a schema without any nesting. The next example, I hope you can see my screen. I can see here. This is a bit more involved, wherein we are showing examples of how to use collection or container data types like list or map. Again, device ID, device type, those are mandatory fields. The tags, repeated means there can be 0 or 1 occurrence, which means it's optional. And to encode a list, you put it within a group. What that means is that now my measurement can have an array of values. Say for channel ECG, I could pack in a bunch of floats. Now introducing Apache Parquet means that you have an extra phase in your pipeline whose primary requirement is to convert the row representation into a columnar representation. Here is a sample workflow for how you would build such a pipeline. You can the first step is the event still sending data in the original format, which is a row-oriented style. Could be Avro or plain JSON. And say you have a microservice, that's receiving those events, which does the validation, normalization, or any other transformation. And once the transformation is complete, you can queue it to a Kafka topic. There is a new library from Kafka guys, which allows called schema registry, which allows you to validate any message that's sent in Avro format. So before queuing it, itself, you can know the errors then and there. And once the events are queued, now you can have a Flume agent. All it does is it listens to the events real time, and then it can write the data onto HDFS. You could replace Flume agent with Kafka Connect here. The advantage with Kafka Connect is that your writes on the sync side is exactly one semantics, something you may want to consider. And once you have the serialized Avro data or the raw data onto HDFS, you can have an MR converted job which will convert the row representation onto a columnar representation. You could alternatively replace this MR job with a Spark job as well. It's up to you. And once you have the data in columnar representation, you can run your hourly or daily Spark jobs, or maybe a different job, based on whatever threshold it's supposed to run. And persist onto a sync of choice could be Cassandra, or writing back to HDFS. As I said before, the important factor here is not only just the storage savings, but also the query performance. Based on our test, for some of the batch jobs, we found that the performance improved by 3 to 4x than running through the sequence file-based formats. I guess I can skip this slide. I was trying to convey that in a batch model, if a job fails, you can replay on its entirety. So if exactly one semantic is critical and latency is acceptable, a batch job based pipeline would be a good fit. The second section that I want to talk about was a new feature that was introduced in the recent versions of Cassandra. The feature is called SASI. SASI stands for SS table attached secondary index. What this allows you to do is that previously you couldn't, your Cassandra database didn't have a rich enough support for compound queries. So you had to rely on Elasticsearch in the past. Now Cassandra can do that job for you. Let's look at some of the examples that wasn't previously possible in the earlier versions of Cassandra. The first feature was that you can do prefix matches. Say I can get all messages or events for the PPG channel. You can do contains class, which allows you to do infix based searches. You can plug in different types of analyzers. Out of the box, Cassandra has support for non-tokenizing analyzer if you want to do a term based search, and then you can also plug in a standard analyzer. If you use a standard analyzer, you can put in things like what locale you're targeting, whether you want to enable stemming, whether the search should be case sensitive or not, and if you want to discard stop words. All of this functionality can now be done in Cassandra starting version 3.4. Lastly, you could do sparse queries. Sparse queries make sense when you have unique value, say on a temporal data. You can now do range and equality searches. As far as the life cycle of the SASI index metadata files, it follows very similar to that of Cassandra's SS table. What this means is, hey, my client sent a write with say consistency level of local 1. The data gets the replica or the primary which is supposed to receive the data, it will write it onto the commit log, then it will write it onto the mem table, and then send an acknowledgement back to the client, or it may be sent to the coordinator. If you use a token aware policy, the client gets the confirmation. So there is a one less network hop that you can avoid by using token aware policy. Now, if there is a SASI index associated with the Cassandra column family, it does an extra step of maintaining your in-memory index structure. And when the mem table gets full, what it does is the data that's in mem table gets flushed onto SS table, and similarly the data that's in the in-memory index structure gets flushed onto a SASI index file. So you have a one-to-one correspondence between Cassandra SS table and the SASI index file. So the life cycle is just the same, as I said. And now during compaction, what happens is that when multiple SS table files get merged, the associated SASI index files also get merged. It's a pretty cool feature. We are yet to use this in production, but we have tested it on a fairly good amount of load, and we liked it, and most likely we'll be deploying this in prod. There are a few caveats that you need to consider when using SASI, and this applies in general to secondary indexes as well. When you use secondary index in Cassandra, it is very important you provide partition key. If you don't provide a partition key, the query will be submitted to every node in your cluster, and you can't scale linear anymore. Same caveats apply to SASI index as well. There is no support for sorting. So if you are working on a time series data and you need sorting because the users would like to paginate real time through some kind of an API, you have to move the sorting onto the as a clustering key. There is no support for scoring. The third one, which I think I found interesting, is that it requires 2 passes to fetch your data. First pass to read the index file, and second pass to read the actual data. So search engines have a bit of an advantage here. And if you have very wide partitions, then SASI only maintains the partition offset. From there on, it has to do a linear search. Some caveats that's worth considering. Okay, I guess out of time.
I just wanted to make sure we get some type of questions.
Okay, I was just going to conclude that we have a couple of examples of how you would use SASI index. The first one demonstrates how you would create a prefix-based search using a non-tokenizing analyzer. So you can do searches like this guy here, the prefix match. And the second example allows you to do infix-based search. And you have the option to specify your analyzer, and if you want to enable stemming, or if you want to enable your locale or skip stop words, and how you want to normalize the data that you're indexing. I guess I'm not going to have time to discuss streaming primitives, but the takeaway is that you can now react in a very low latency way. Okay, I guess I will stop here and take time for questions.
I had a question about the streaming primitives.
Mm-hmm.
Yes, maybe we talked about it now. So if I'm building an application on the cloud platform for IoT, then what are the ways in which I can receive streaming events from the platform?
Can you repeat the question?
So if I'm building an application that requires streaming events from a device, let's say a car, one of the other support devices, what are the options for consuming that as an application?
So the question is what options you can consider when building your stream processing from an IoT perspective. So today we have Apache Spark streaming, or you can use Apache Sansa, or you can use Apache Flink. Spark streaming as of version 1.6 does not have support for event time processing. They are going to add that feature in 2.0, but then when you are windowing based on event time, you need the notion of completeness, and they haven't yet documented how they are going to handle messages which arrive late in the pipeline, so that you still emit results in a speculative manner. Flink has out of the box support right now. I would say Flink has a bit of a momentum right now because of the rich primitives which it built based on Google's data flow.
So you mentioned that you're stacking a lot to do in Scala. Did you find there were nice things about Scala? Scala works and
Yeah, I was originally a Java developer. Scala does take some time to learn, but we found that there is definitely some savings in terms of code size. The test libraries like Scala test are awesome, and and even as far as the frameworks, Play is pretty decent. Finagle is even better. So as far as the libraries are concerned, it's fairly rich, and you have some very good options that you want to consider.
Thanks.
Okay, cool.